Okay, let's make a start. It's fascinating listening to all these multiple conversations going on. I'm picking up all sorts of interesting stuff. I shall use it later when it comes to examination purposes. Hello, we can still hear you. Hello, I'm here. Thank you. Right, what I want to do is continue talking about some of the things that we introduced in the last lecture. And I want to move away from the sort of the overall view that I tried to give you in the first place, and try and put some detail together. Now, some of you did 20712 last year, and will have seen some of this material in very compacted form before. Well, although some of you to some of you it'll be completely new. So what I'm going to do is I'm going to go through the material to describe the sort of the physical basis of the atmosphere. Then we're going to talk a bit about chemistry in the next couple of lectures. So what I want to try and get through today is first of all some ideas about how we measure things in the atmosphere, and then also to put some detail on the structure, the temperature, and things that stir the atmosphere around. Okay, so we're going to start with observing the atmosphere. So, what do we need to measure? The first things that we need to establish are things like the composition. So we need to know what chemicals are where. We need to know the physical parameters like the temperature and pressure, because the reactions that we're going to be dealing with are gas phase reactions, so they're going to be involving things like collisions between molecules, and collisions between molecules scale with the pressure. So the higher the pressure, the more molecules per cc, so the more likely the collisions are. So that's a very important thing in gas kinetics. We also need to know the temperature, because many of the reactions that we're looking at have a barrier. So if they have a barrier, there's an Arrhenius factor, so the temperature will help us understand the kinetics there. But what we also need to know are things like atmospheric motion, so we need winds, and we need to know things also about clouds, water vapour, so to understand some of the problems that we discussed in the first lecture, we're going to need to make a series of measurements. So how do we make these measurements? Well, there are lots of different ways of making measurements. So first of all, there are lots of kinds of measurement. We can look at point values, at a fixed position. We can look at track values, which is along a path. We can look at column values, well, a vertical column. And all of these kinds of measurements have to be done in a certain way that we can then use the data that we obtain from them to understand various of the processes. Okay, so these measurements give different kinds of data. Some point data, if you're trying to do global atmospheric chemistry, isn't necessarily what you want. You want track measurements or column measurements. Column measurements don't allow you to look at small scale variations they only allow you to see the total. So we need to decide what it is we want to, the way in which we want to measure something, based on how we want to go about trying to understand the various different processes. Okay, so the key thing about this is when it comes to understanding the various different components of the atmosphere, what we're going to do about it, we need to think, before we start off on our atmospheric study, we need to think about what we want to measure and how we're going to model it, because the things that we measure need to be the sorts of things that we can model. Okay, so there's no point, for example, having a chemical system that we can model with a load of gas kinetic equations that predicts some composition at an instantaneous point if we're comparing it to column models, so column measurements from a satellite, for example. Okay, so there's no point in predicting column values and then subsequently comparing them to point or track values measured in the field. So predicting obviously is models. So how do we go about doing this? Now let's have a quick look at the. No, it's not a big. Yeah, that's a long one. So what I'm showing here are a few of the different ways in which we can make different kinds of atmospheric measurements and the way that we do make measurements. Each of these give different kinds of information. So the first thing we've got here is we've got aircraft. This is the Facility for Airborne Atmospheric Measurements. This is based in Cranfield, and this is a BAE 146 fitted with lots of different instruments in the fuselage and also some detectors based on pods in the wings. So what this does is it flies through the atmosphere, and at certain altitude or a certain track, the measurements that are made there are then compared to models of using wind speed and such like that. So this is a moving path or track value. Here's another way of doing a track value, and that's to take something like a ship and put a measuring package in a relatively free part of the ship. So if you were making some measurements from a ship, you'd want to make them up to the top somewhere, so that you were making sure that you weren't sampling from the exhaust of the ship, which obviously would show you quite a lot of carbon and soot. So even when we decide we want to do a track measurement, we also have to think about whereabouts in the atmosphere we want to get to. So we can also make point measurements on the ground, and these are the most common that are made. This is Mace Head in Ireland, and this is right on the west coast of Ireland. There's a little measurement station on the end there, and this samples air coming in from obviously from 360 degrees, but the predominant wind here is from the southwest, so this samples relatively clean marine air and gives us some idea of what's going on in the lower part of the atmosphere. Whereas this one here, this is the Jungfraujoch in Switzerland, and this is very high up. This is about 16,000 meters up, so this is sampling into the free troposphere. So it's sampling different parts of the atmosphere. Just put some of that down there. That's for you. So these sample track values. So we can fly this. We decide a flight pattern. An example of something which we'll talk about in some later lectures, so I won't go into too much detail now. What we do with this is we tend to have a series of instruments and then look to see things like the plume of pollution from a big city, so you can fly backwards and forwards across the plume at different altitudes out to the outfall of London or Birmingham or something like that. So this gives you the possibility to sample lots of different parts of the parameter space for a given event. What the ship ones do is that they measure, so this measures from around about 50 metres up to around about, well, you can get up to about 10 kilometres with some planes reasonably easily. This ceiling of this one's about 6 kilometres, I think, something like that. So this samples from the bottom of the troposphere to the tropopause. And we'll see what these terms show in the middle. So this is quite a large proportion of the atmosphere, and we can decide lots of things to do with that. On ship-based ones, again, we don't have much ability to decide the flight pattern, but what they normally do is that they put these on commercial ships. And commercial ships follow well-established shipping lanes. Follow the different shipping lanes around the country, around the world rather. And this samples a different part. This samples typically about 20 metres, and specifically because it's ships, what it's sampling is what's called the marine boundary layer. Okay, so as your ship goes around the world, it's constantly sampling at 20 metres above the sea, so it's getting all the chemicals that are associated with emissions from the sea. These ones here, this is, as I said, this is Mace Head, and what this samples is it samples the marine boundary layer, which is usually clean air from the southwest, the predominant winds blowing over that part of Ireland are from the southwest. So this is, and they've come across the Atlantic, so it's about 3,000 to 4,000 miles from the nearest land. So most of the chemistry that would be going on from balloons from Central America and from North America have disappeared by the time they get there. So measurements like this are really good for letting us know what the background sound signal looks like. So if we want to do pollution studies of cities, we want to know what's there naturally in addition to what we put in it. So we need to know what the background looks like. This one here in Switzerland, the Jungfraujoch on the top air, this is sampling, again, it's sampling clean air, but this is sampling from fairly high up. This is sampling from what's known as the clean troposphere. And we'll look when we see, when we talk about the different sort of layers in the atmosphere, that this is another part of the atmosphere where most of the pollution hasn't got to. So it gives us some indication of what the chemistry should look like in parts of the atmosphere when the pollution is relatively low. So we can sample in different parts of the atmosphere, and we can do it in different ways with different kinds of instrumentation. And then we have to have our models, and our models need to correspond to the sorts of information we're measuring, so we can then develop an understanding. Okay, so we need to decide which parts of the atmosphere to measure. We've got the bottom of the troposphere, we've got the marine boundary layer. We have the lower troposphere, which is about the bottom kilometres. So from the surface to about 1 kilometre. And we distinguish this from the marine boundary layer because this is over land, so that there's different kinds of emission. Okay, and the free troposphere is the bit of the high atmosphere above most of the pollution. So this gives us a good indication of sort of background kinds of chemistry which are going on. And there are various other different distinctions. We'll talk about urban versus rural, polluted boundary layer and things like that. But these are just general areas where we're going to concentrate our observation. What we also need, when we're going to think about the amount of the air that we're sampling, we need to think a little bit about how much we've got of the Earth that we can calculate, that we can investigate. And some basic parameters that we need to think about is when we come to actually think about the planet itself, is thinking about how many molecules we're actually dealing with. Because we think of the atmosphere as being a thin, dilute gas, but actually it's quite a significant thing. So the mass of the planet itself is 12.74 times, sorry, get my numbers right here. The diameter of the planet is 12.74 times 10 to the 6 meters. The mass is about 5.97 times 10 to 27 kilograms, and it's surrounded by a shell of atmosphere and the atmospheric mass is about 5.14 times 10 to the 18 kilograms. So compared to the mass of the planet, it's a relatively small amount of material, but actually 10 to the 18 kilograms is an enormous amount of material. Okay. If you compare that to the total mass of the human population, some estimates were made in the early 1990s about this. It's about 3 times 10 to the 11 kilograms. So actually, the total mass of molecules in the atmosphere is greater than the total mass of all the billions of people that there are on the planet. I don't think they made this calculation on average weight by me. I think that it'd be about 5 if they scaled everybody up to my size. But it's still quite a large amount of material, but it's insignificant compared to the amount of air in the atmosphere. And if you turn this kilograms into moles, you'll see that's about 10 to the 21 moles of material. So there's quite a lot of material present in the atmosphere, so we need to think about how we're going to quantify it. Okay, so we'll start off with units to describe atmospheric parameters. We'll start off with the simplest thing, obviously temperature. The temperature starts at room temperature, at the ground level. It goes up and it goes down in various different parts of the atmosphere. So we always use atmospheric temperatures in Kelvin. It saves messing about, and it makes it much easier to do our numerical calculations. Now with pressure, we have a number of units of choice. The simplest one, obviously, is the atmosphere. 1 atmosphere. But we also find that we need to express this in different kinds of units. So, for example, 1 atmosphere is, in SI units, is 101.325 kilopascals. So the pascal is the SI unit of pressure. So obviously we'd like to try and do our measurements in pascals if we're going to use other things, but we find that there are other units. So 1 atmosphere is 101.325 kilopascal, but this is 760 torr, which is millimetres of mercury. You sometimes find this used in old instruments, for example, still. Just the Americans like it still. But also we have things like a millibar, so 1 millibar is 1,000th of an atmosphere, etc. So we have to, if we're going to do calculations based on this, we have to think about the units that we want to describe things as. Now pressure becomes a little bit more complicated. Temperature is something which all gases experience. They all, in the same local thermodynamic equilibrium, they all experience the same temperature. But the concentration of gases and its relation to pressure is something that we need to express in a rather more complex manner. Okay, so quantities of gases are best expressed as a proportion of pressure. I'll show you why now. So let's just go back to a slide. Here's a slide showing the variation of temperature and pressure with the atmosphere. We'll talk about the temperature in a minute, but what you can see is that the pressure goes down sort of exponentially as a function of altitude. The temperature goes down, and then it shows some different, some inflections. So this temperature is something that we can monitor quite easily. The effect of pressure going down with altitude has quite a dramatic effect and quite an important effect on the rates of chemical reactions. So we need to find out, first of all, how to describe the pressure, and then how we describe concentration at different pressures. So the thing that we do in chemistry is we do everything at atmospheric pressure when we're doing work on the bench. But if we're doing reactions at, say, 10 millibar, that's going to be different numbers for a given number of molecules. That's going to give us different pressures, different reaction rates. So we need to find a way of describing that in reasonable detail. So let's go back to. So we normally describe the concentration of materials in the atmosphere by what's called the volume mixing ratio. And what that is it's based on the fact that Avogadro's principle. Okay, look this one up if you can't read my writing. So, Avogadro's principle says that equal volumes of gas at constant temperature and pressure contain equal numbers of molecules. And what that means in reality is that if you have a litre of methane and a litre of oxygen, there's the same number of molecules in the litre. And it's true for perfect gases to a reasonable extent. Okay, so back to basic first year properties of gases. From the perfect gas equation of state PV equals nRT, we can rearrange that to obtain N over V, which is the number of moles per unit volume, is P over RT times Avogadro's number. And the important thing that we're going to want for chemistry here is we're going to want the number of molecules per unit volume. So these have the usual thing. So this obviously has to be in pascals, this has to be the gas constant, this has to be in Kelvin, and this is Avogadro's number. So if you do that calculation, at standard, what we're doing at standard ambient temperature and pressure, which is 1 atmosphere and 25 degrees C. So 25 degrees C is 298.15 Kelvin. We get N over V is equal to 2.46 times 10 to the 19 molecules per centimetre cubed. Okay, that's any molecule. So if we take a centimetre cubed of gas in the electric theatre, as long as it's at room temperature, then we'll get 2.46 times 10 to the 19 molecules per cc. Now that's a number you should remember. You'll need to calculate it, you'll certainly need to use it lots of times. That's an important number to remember. Okay, so we can then express the concentration of any gas as a proportion of this number. So by that I mean, if we have something that's at the partial pressure, so a partial pressure of gas A is 1 millibar, in a total, and the total pressure of gases is equal to 1 atmosphere, or let's say 1,000 millibar to make the calculation easy. Because of the Avogadro's principle, we say that gas A is 1,000th of the total. Okay, which means effectively this is 1 part per 1,000. So 1 part per 1,000. If we turn the calculation the other way up and we work out the concentration in parts per whatever, then we can turn part per 1,000 into number of molecules by taking. So this is at some particular temperature. So we can take at any given total pressure, we can calculate N over V and multiply by the volume mixing ratio to get the absolute number density. So we have N over V, some particular thing, multiplied by the volume mixing ratio gives what we call the number density. I'll show you some examples of this in molecules per cc. So for example, 1 part per 1,000 is equal to, at a room temperature, sorry, let's say Tp, is equal to 2.46 times 10 to the 19 times 10 to the minus 3, that's 1,000. It equals 2.46 times 10 to the 16 molecules per centimetre cubed. So if we know the volume mixing ratio and we know the pressure and the temperature of the atmosphere, we can calculate N over V, and that means that at any altitude in the atmosphere, from the volume mixing ratio, we can calculate the number of molecules. Now, the reason that this sounds a bit like a around the houses way of going about doing things is it's quite often easier to measure the proportion of something with respect to something else, rather than measuring absolute number concentrations. Now, the reason that this is important is that trace gases are normally present in very, very small quantities. And if we want to know the significance of something, then we need to know their relative concentrations. So the ones that we tend to use are parts per million. So that's ppm. Parts per billion. ppb. And parts per trillion, ppt. So 1 ppb is one molecule in every 10 to the 9. So here's an example of some of the sort of values that we get for this. So here are some common constituents of the lower atmosphere, and we can see mole fraction here. The thing I should have mentioned is that the parts per whatever is effectively the same as the mole fraction. So this is why it's useful in chemical terms. So we start off with saying, well, nitrogen's 78% of the atmosphere, so it's 0.781 as a total mole fraction, or 781 parts per thousand, or 781,000 parts per million. Okay, those are big numbers, we don't want to deal with those. But when we get down to the sort of reactive components of the atmosphere that we're going to be interested in, things like things like methane, and N2O, and CO, and ozone, and ethene, and you can see parts per billion gives us much more usable, user-friendly numbers in order to describe these kind of values. So we tend to use these kind of values because not only do they give us the proportion, they also give us nice workable numbers. It's the same sort of principle that we use wave numbers for infrared because you get 4,000 to 400, and we use nanometers for UV visible because it gives us 700 to 200. It's the same sort of principle. We like to keep our numbers small. But in addition to this, it also gives us relative importance. So it's equivalent to mole fraction. Oh yeah. Okay, so this gives this is equivalent to mole fraction and gives relative concentration info. Okay, and the reason that that's important is that we can usually measure relative values more easily, as we shall see when we come to describe things. It also shows us about the relative concentrations of things, and sometimes their relative importance, but it depends very much on how reactive they are. So an example I'm going to give is ozone concentration. ozone concentration versus altitude. Now, ozone is ubiquitous throughout the atmosphere. There's ozone at the ground level, in the troposphere, in the bit that we inhabit. There's ozone in the free troposphere, and there's also ozone present in the ozone layer at an altitude of 15 to 25 kilometres or so. And we know it's important, but it's the parts of the atmosphere where it's more important than other parts of the atmosphere. So if I just go back to this slide, what you can see on here is we've got two graphs here. One of them shows the concentration of ozone expressed in terms of number density. So this is atoms, molecules per cc. And you can see it's reasonably constant through altitude. So this here shows altitude, by the way. This isn't a very good diagram, is it? So it's altitude on this side, it's pressure on that side. So as we go up in the atmosphere, we see the number density stays with 10 to the 12 or so 10 to the 12 molecules per cc, and then it starts to tail off when we get above about 40 kilometres or so, for reasons we should discuss later. However, if we look at the mixing ratio, so this is the volume mixing ratio of ozone, what we see is the volume mixing ratio is virtually nothing. It's not actually virtually nothing, it's just the scale here, so this is parts per billion. If you look here, the volume mixing ratio of ozone, this is for the troposphere, is between 20 and 80 ppb, typically. So 20 and 80 ppb on this scale is virtually nothing. But as you go up in the atmosphere, this same number of molecules per cc, actually because the pressure is going down, the number of molecules, the volume mixing ratio shows a massive increase, up to about 8 ppb at the maximum of the ozone layer. So what this is telling us is that 10 to the 12 molecules down here is a very small concentration, but 10 to the 12 molecules at this part of the atmosphere means that this is a very, very major component. In fact, what it's telling you is that there are, because it's in parts per million, this tells you that there are 8 ozone molecules per million total molecules, and that's quite a lot actually. That's quite a high concentration of things in the atmosphere. So this is why the ozone layer is, this in part explains the significance of the ozone layer. Although the concentration in molecules per cc is about the same in the ozone layer, it's actually a much, much larger proportion of the total. No, try again. Okay, so we've got the volume mixing ratio is about 8 ppm at 25 kilometres, and it's 50 ppb at 0 kilometres. So it's a much more important, relatively more concentrated species. And in fact, it's the concentration of ozone and the chemistry that goes on that actually is responsible for keeping the stratosphere hotter than it should be. So that's a brief introduction into how we describe the concentrations of things. What we now need to do is have a quick look at some of the spatial and temporal scales upon which these things occur. Okay, so there are a variety of ways in which atmospheric composition can change. There are, in some cases, there are chemical cycles, and in some cases there are emissions. And emissions So chemical cycles are cycles of chemistry that goes on in the atmosphere, translating one material into another. Emissions are things which come from the surface of the planet, and there are a number of different ways in which these emissions can occur, and the two things that we're going to be interested in are what we call biogenic emissions and anthropogenic emissions. So biogenic means things that's emitted from stuff to do with biology. So this is gases which come from animals and plants, bits of animal and plant, spores, all that kind of thing. Anthropogenic emission is stuff that generally comes from man's activity. There are several points to notice here. Okay. Some species have both biogenic and anthropogenic sources. So that means that there is something, so they're emitted naturally, but they're also emitted by industry, agriculture, that sort of thing.
The doctrine supposed to say anthropogenic.
It's supposed to say that some species have both biogenic and anthropogenic sources.
Yeah, because above you wrote anthropogenic.
Oh, right, sorry, I spelled it wrongly up there. Okay, so some species have both biogenic and anthropogenic sources. Some biogenic species are emitted due to increased activity by mankind. And we're having a good day today, aren't we? So what I mean by the last species, the last thing there, is that we might, for example, think, well, one of the main biogenic sources of methane is from plant life and wetlands and rice paddy fields and things like that. So the more we turn our land into agricultural land, the more we get methane being emitted from what would be considered a biogenic source, but it's because agriculture's expanded it. And a classic example of that is expanding agriculture. And there are a variety of different kinds of chemical cycles for the various different important components. So what I've got on this slide here, the next slide, is a description of the various different kinds of species that we observe in different parts of the atmosphere. So what this thing here shows is it's individual gases, the molecular weight of those gases, the average mixing ratio, the volume mixing ratio in parts per million, and the cycle, don't worry about the status, we'll talk about that in a minute, whether they undergo cycles or not in the atmosphere. Okay, so things like the rare gases here, argon, neon, krypton, xenon, they're present in the atmosphere in reasonable concentration. They were formed during the Earth's history, but they're not really transformed into anything, so they don't react with anything. So the concentrations of these things generally stay quite constant. Things like oxygen and nitrogen are present in large quantities, and they have both biological and microbiological cycles. So what this means is that there are some things which can change the concentration of oxygen and nitrogen in local systems. This is plants taking in oxygen, animals taking in oxygen, nitrogen fixation by plants. That means that emissions of biogenic nature are affected by cycles, biological and microbiological cycles. Professor Livins will do quite a lot more about this with you in his part of the course. Then we go down to some of these things like methane and CO2 and CO, and these have both biogenic and anthropogenic sources, but they also have chemical cycles in the atmosphere. So what this shows is that they have mostly biogenic sources, but they also have chemical transformations in the atmosphere. CO has anthropogenic and biogenic sources, and CO2, and CO has largely anthropogenic sources. It's not really emitted by biology, but it also undergoes chemistry in the atmosphere. So what we find is for a majority of these lower, what we call trace species, we find that the concentrations of them in most parts of the atmosphere are in equilibrium or quasi-steady state. And what that means is anything which affects either the biogenic sources or the anthropogenic sources or the chemistry can change the relative concentration of these different gases. So let me just go back to... Okay, so what we have for a number of the important species is we have emissions, we have chemistry, and then we have sinks. And some of the sinks may then end up creating the arrow goes in that direction. Some of the sinks where the materials have undergone chemistry and then gone to ground may also then end up being emission sources, but not necessarily of the same material, but we'll deal with that in a different lecture. So what we have is cycles of materials, and because we have cycles of materials, that means that any changes in any of the emissions of any of the species can potentially have an effect on any of the others. And this is predicated on the fact that you'll, being chemists now in the third or fourth year, you'll realise that equilibrium is a dynamic phenomenon, not a static phenomenon. So by that we mean that although we may have, in a chemical reaction we have 100 moles of product and 1 mole of reactant, things are still going backwards and forwards all the time. So we've got lots of systems where equilibrium is a dynamic problem, and this implies features such as feedback. Unless we understand all of the processes and how they are interlinked, models will be inaccurate. Okay, so what we've got is for any given chemical species, we've got emissions, we've got chemistry, we've got sinks, and then we've got the effects that their chemistry has on other things, so that's just a one-dimensional thing, multi-dimensional, and also these things are linked together so that they all vary with each other. So if we change the concentration of one thing, we may see some changes in the concentration of other things, but because these things have also like a feedback effect, we may change the concentration of another thing, which may then have an amplified effect on the concentration of other things. So things in the atmosphere can go quite a long way from equilibrium fairly quickly by relatively minor changes. So we need to have our models having all these interlinks. So we need to know all the chemical species. We need to know how all the interactions are interlinked within these chemical species as well. Okay, we better finish there for today.